Wednesday, August 20, and Wednesday, August 20 as well. But first Wednesday is Tuesday. Okay? Thank you very much. Our next speaker is Professor Vladimir Fock from Strasbourg, France, and he will talk about cluster varieties and integrable systems. So welcome.
Thank you very much. So I'll speak about one particular class of integrable systems, actually, well, which come from cluster varieties, and I'm not supposing you to know what is cluster varieties. Well, maybe it's better to know a little bit what an integrable system is, but what I'm going to do is just construct explicitly these integrable systems, and, well, since I have a text submitted to the proceedings of the ICM, so I'll, instead of giving you a theory, I'll speak about practice. Namely, I'll construct explicitly some example. And on this example, well, actually, it's, you can make a theory yourself. So it's, I hope to be not very, not very advanced and understandable. So they just warm up. I just recall some very simple thing which is known for ages and even, well, included somewhere in the program at high school, but sometimes not in every country. So, for example, in my country it's not. So this is the Pick's formula. The Pick's formula is just a formula which relates, in Germany it certainly is. So this is, and the Pick's formula is formula which relates the area of a polygon on a plane with integral vertices with a number of integral points inside and on the boundary of it. So let's, delta will be a convex polygon on the plane, and the number of, I delta is number of integral vertices inside the polygon, B is number of integral vertices on the boundary, and S it's in the area. And they are related by the relation then twice the area is twice the number of points inside plus the number of points on the boundary minus 2. Well, easy exercise to prove this formula, and the example for that is just you have this quadrilateral, the square, and you have just the area is equal to 2, twice 2 is, the 1 point I is equal to 1, and P is equal to 4. So you can verify that. Now proceed to integrable systems, and actually this formula will play a key role in this integrable system. So the cluster integrable system is not my construction. This was constructed by Kenyon and by Goncharov and Kenyon. And what is that? It's just a map. So it's a map from one space to another. The first space is, well, both spaces are really very simple. The first space is just a power. It's an algebraic torus, so it's just a power of a multiplicative group, and for simplicity I wrote it just as C star. And the second is essentially almost the same thing. It's just some copies of C, some copies of C star, and then quotiented by some multiplicative group of dimension 3. So the main property of this map is just, first property that the manifold X, I meant the pointer. The manifold X here is not just any manifold, but, well, it's provided by very simple log constant Poisson structure, and the B has a Poisson structure, but it is 0, and the map has such a property that, first of all, that any functions which are lifted from well, first of all, this map is a surjection, then you lift two functions from B, and then they Poisson commute, and then this family of Poisson commuting functions is maximal possible, given by this map. You cannot add any function which commutes with everybody. So everything which is which commutes with all such functions, they are in this class. And well, this property implies that if you take any point in B, then inverse image of this map, well, is in general a Lagrangian submanifold of X. But since, well, this mapper is, well, in this particular case, this will be just a torus, and the torus, not any torus, but a Jacobian of algebraic curve. And the Pick's formula, which I started with, justifies this possibility, because you see that the the dimension of the torus, which is equal to I, is equal to the the dimension of the base minus the corank of the Poisson bracket. And I forgot to mention that the dimension of the space here, the dimension of the space X, will be twice the area of this polygon. So it's numerology works well. But, well, you may even forget now about all this theory. Let's go to practice. So, instead of constructing an integrable system starting from a polygon, I'll construct an integrable system starting from another object. Namely, well, now I pass to my main example, and namely, I'll construct an integrable system out of a bipartite graph on a torus. So we have a just two-dimensional torus, and on it you have a bipartite planar graph without intersection of edges. So in my example, it will be this graph. So it's also not on a torus, on a square, but you imagine that the top is glued to the bottom and left to the right. So we have just a bipartite graph, and out of that I will construct an integrable system. And on the other hand, I will construct a polygon, and you will. Well, in fact, this construction can be inverted. So, though it's not, well, it's just to be more understandable, I did it in this order. I could do just starting from a polygon. So, well, now first I construct my space where this integrable system lives. And this space will be the space of, I just attach one variable to every face of my graph. So I have 4 faces, 4 variables, and I impose the condition that the product of these variables is equal to 1. This will be my face space. And this space should be interpreted in the following way. So on the graph, as also like on smooth surface, you can construct connections. So imagine that you have at every point of the graph, you have a vector space, one-dimensional vector space, and on every edge you have isomorphism between the corresponding vector spaces. So you just can take its one-dimensional vector space and carry around the graph, following the isomorphisms. And you can take a vector space around the face and return, and it will give you a monodromy. It's just a discrete analog of a curvature. And so these numbers should be understood as a kind of discrete curvature of your connection. Now, on this space, there is a canonical Poisson structure. And the Poisson structure combinatorially is described maybe in the simplest possible way. So instead of writing, well, in order to write down the Poisson structure, I first draw a graph, with these pink arrows, which show the, and from this graph I will write down the Poisson structure. So the idea is that these pink arrows are just the edges of my graph rotated 90-degree counterclockwise. So if I imagine that my arrows of the graph are oriented from white to black, and then rotating gives me this arrow, for example. And then I get this graph, and and the Poisson structure written like that. For example, between x and y is equal to x times y times the number of arrows going from y to x. Here we have one arrow going from y to x and another arrow which goes around. And for example, the Poisson bracket between x and z is 0 because there are no arrows going from x to z. If I just forget the graph and keep the arrows, then I get this very simple quadrilateral which encodes my Poisson structure on the right. So this is really something very simple and combinatorial. Now I need to do some, well, not very important actually thing, but nevertheless it should be done to be precise. So I need to paint some edges in red, and it's called Castelline orientation, and this is done in the following way. So I need that somehow the red edges will be considered as edges with weight -1, and I need to do that in order to ensure that the number of sides of every face be equals to 2 mod 4. So every edge is quadrilateral, so it's not 2 mod 4, it's 0 mod 4. But if I count this edge, for example, but with coefficient -1, then the total number is 2. And this is 2 mod 4. And you can easily prove that you can do it always for any graph, and the NB-Bartlett graph of the torus, and essentially the answer does depend on the way how to do that. There is also, you can do it some way. Now I want to construct, I construct a space, now I need to construct a map to another space, which will be my integrable system. And the map constructed is the following. First, I mentioned that I understand these variables as curvature. So it's monodromy around the faces. Now I want to lift them really to isomorphisms. So what I did here, I imagine that the edges without labels are just with labels 1. So for example, if I go around this face, I go here I have 1, here I have 1, here I have x, here I have 1. So the total monodromy is x, which is correspond to the monodromy here. Here I have, for example, I go here, it's xw. I go here, it will be x, but since I go from white to black, I just need to divide, not to multiply. Then I go 1, 1, and the monodromy is w. Here, the monodromy is xzy, but xzw, but since the product, it's minus, sorry, xzw inverse, but since the product of all variables is equal to 1, then it's equal to 1. And this is, it can be done in several possible ways. I don't see that it's unique, but I can do that. So I just lift to curvature to connection. Then I keep going, and now I want to emphasize that really, if you have a curvature, then it doesn't determine a connection, because if you have two one forms, then they are two exact forms. Then the d minus 1 is determined up to an exact form, a closed form. Sorry. So otherwise, you have plenty of connections which have monodromy 1 around every face, but not trivial monodromy around cycles of the torus. I have 2 cycles, so here I constructed a labeling which really doesn't contribute to this monodromy. So for example, you go around this face, every time you have mu here and mu inverse here, so the product is 1. The same thing, product of lambda inverse is 1, so monodromy around every face is 1. But if you construct a monodromy around a non-trivial loop, for example, you go from here to here, you have 1, here you have lambda. So the monodromy around the loops is non-trivial. Well, now I can multiply both and get a monodromy which, these variables, black variables, numerate the monodromy around faces, and blue variables numerate the monodromy around cycles. So there are two, different variables. And then I'm going to construct something which is in continuum limit. If you can take graph you refine the graph, tends to Dirac operator. So I call it, for this reason, discrete Dirac operator. But it's really, I don't know, I'm not going to go to continuous limit. this matrix, which is the simplest possible I can imagine, constructed from this picture. So you have two white vertices, two black vertices. Remember that these two vertices are glued together, so it's one vertex. The same thing, the corner vertex is another one. So, for example, if this vertex is number 1 and this vertex is white vertex number 1, then they are connected by two edges, one with lambda and one with 1. And therefore, on this 1, 1 element of my matrix, I have 1 plus lambda. Here, for example, these two edges are connected also to two vertices are connected also to two edges, this one and this one. But since these edges are red, I put minuses in front of that. So I get kind of lattice, well, it's similar to lattice Laplacian, but since they are signs, it's not actually Laplacian, but it's Dirac operator. And, and I can take a determinant of that. So this procedure defines me what I want to say. It defines me an equation. See, so if you forget about, determinant is just function of two sets of variables. One is black variables and blue variables. Black variables, so two blue variables. For any graph, it will be always 2, lambda and u, and plenty of black ones. And here there are 4 of them, but in general you have more. And it defines me, if I just consider black variables as parameters and blue variables as variables, then you get an equation of an algebraic curve. So this is an algebraic curve, and the coefficients depend on the black variables. Now, with this data, I can construct both my base space B, base of my integrable system, and the Hamiltonians. So, and also the convex polygon, which I started with. So what's complex polygon? It's nothing but just a Newton polygon of this function which I constructed, determinant of the Dirac operator. So you have I put, for example, x is a coefficient at mu. So I put it at this point because it has it corresponds to power. Here is the monomial at x is mu to the 1, lambda to the 0. So I put to the point with coordinates 0, 1. And I distribute these coefficients, and then I take convex hull of all the points where I have something non-trivial. So I have a polygon, and this is actually my polygon which determined my system. It's just some theorem which tells that all systems, all graphs giving the same polygon are actually given as isomorphic integrable systems. So I have these functions, but some little problem that these functions are not actually well defined, because you can take another lift of your connection of your curvature to the connection. So there are some ambiguities in this construction, and this ambiguity in this construction amounts to possibility to multiply lambda by any function, lambda by something, mu by something, and the whole function by something. Geometrically, one can imagine that you have a curve in c star squared, because in lambda and mu are just coordinates on two-dimensional space. And on this two-dimensional space, you are allowed to apply symmetries. So you can multiply one variable by a constant, another variable by a constant, and also you can multiply the equation of the curve as a constant, because the curve doesn't change if you multiply the equation by a constant. So these coefficients are actually not invariants of they depend on the construction, but certain linear combination of them do not. In this particular case, there will be two combinations which do not. So I just take product of these two and divide by the product of these two, which I did here. So it's with the x times z, and this is not minus, it's just a piece of this line, sorry. If you take product of these two and divide by product of these two, it will be not depending on the this arbitrariness I had, and this will be xz, and you can check that the xz is actually Casimir, so it's commute with everybody. And another one is just you take this coefficient and divide the product of these two, and you take the square root, and it's also big. Well, I could. It's not very honest to divide by square root because I want to be algebraic, but I could just write the square of it. It's not a big. Well, just to simplify, I wrote it like that. So, therefore, my base space is just a space of coefficients of my Newton polytope. So it's just the number of all points on the boundary and inside my Newton polygon, and divided by this action of three-dimensional group where representation of lambda mu and multiplication of overall constant. So it will be my base space. And this is a construction which allows you can take any graph and make all this procedure and construct a map which is actually an integrable system. Why? Now it's not a proof, but just remark why the inverse images of this map are actually tori. Indeed, if you what means that you fix these coefficients? It means that you fix the coefficients of this equation. And if the coefficients of this equation are fixed, it means that, you have some, it gives you an algebraic curve. But remember that this curve is, the equation of this curve is just condition of vanishing of this determinant. So, if the determinant is 0, the corresponding matrix has a kernel. Yeah.
When you say equation, which are variables and which are constants?
Well, in this particular case, the variables are lambda mu, blue are variables and x and w are constants for a while. But there are blue variables and black variables, sorry. And if you then say equation, I mean x are black constants. So you just have an algebraic curve, but this curve depends on black variables and parameters. So I ask the following question. If I fix the coefficients of this equation, how many, what's the inverse image of this integrable map? So how many, what points, what values of x black variables give me the same curve? And the answer is that from this matrix I can construct a line bundle of this curve. Namely, for any point of this curve, this matrix is degenerate, determinant is 0, so therefore I have a line bundle. And therefore, and this is a theorem that actually the inverse image of the point is the space of line bundles of the curve, and this space of line bundles is the Jacobian of the curve, so this is a torus. So this is a construction of this integrable system. And now a few remarks about some properties of this integrable system. And first property is that what is the topology of this spectral curve? So what is the genus? What is number of points at infinity, etc. So this curve, of course, is a fine curve. It can be complexified canonically by adding points at infinity. And, the standard arguments tells that topology is the following. The number of genus is equal to number of points I delta, the number of integral points inside the polygon. In this particular case, it's just 1. And points at infinity corresponds to the sides of this polygon. More precisely, the segments between adjacent integral points. So if there might be several of them on one side. So in this particular case, there will be just four points at infinity. Now, this construction of the spectral curve is purely algebraic. So we just constructed some matrices. It was an algebraic curve. And, zeros of this function gave me vanishing of determinant of this matrix gave me the condition for this curve. And that's the constructed curve. And actually there is what's nice that this curve topologically can be constructed in purely combinatorial way. And this allows to study this, this integrable system in combinatorial way. So the main ingredient is so-called zigzag or beacon path on the graph. So let's consider a bipartite graph. It can be any graph on any surface, not necessarily torus. And the beacon loop is a loop which goes the following way. It just turns left at every black vertex and right on every white. So it goes like that. And well, this is closed loop, of course, because the graph is finite, so sooner or later you go back. In this particular picture, you have 4 of them. So there are 4 beacon loops, and for every edge, you have exactly 2 beacon loops passing through it, because you can start in one direction or in another direction. Well, these beacon loops are just closed loops, and you can consider homology classes of these loops. So they give you for example, the white loop goes from on this direction. So if you straighten it, it will give you a vector in this, the diagonal vector with this slope, and so you can reproduce it, put it on the lattice, and this is just with the same slope. And so you have a few homology classes, and they sum up to 0, which is obvious from this picture, and therefore they give you a unique convex polygon. And this is convex polygon, the theorem by Goncharov and Kenyon, that this convex polygon is actually coincides with the polygon, Newton polygon of the curve, which is quite non-trivial, kind of also cornerstone of all the construction, that you have combinatorial picture and algebraic picture, and they give the same topology. There is a correspondence between the two. So even you can go a little bit further, and out of this zigzag loop, you can construct the surface itself, so subsurface, topological surface, which turned out to be isomorphic to spectral curve as a real variety. Namely, you can take every zigzag curve and glue a punctured disk to it. So you can, for every curve, I can, for example, for this I glue 1 disk, for here another, etc. I can glue 4 disks. Of course, in order to have something smooth, I need to throw away my faces. So I just construct an abstract graph. I forget about faces. So throw away 4 faces and glue 4 other faces. Of course, for early characteristic reason, in this particular case, it will become also a torus, because the early characteristic doesn't change. Usually it does change, because you throw away much more than you glue back. There are less zigzag loops than the faces, but in this particular case it's the same, so you get another time a torus, and this torus is, and the statement is for a general graph, this torus is isomorphic to the spectral curve. In which sense? Well, in the space that the spectral curve, in that the zigzag loops corresponds to, dual surface correspond to the spectral curve, and the zigzag loops correspond to points in infinity. So remember that in the homomorphic picture I had my points in infinity correspond to sides. Here zigzag loops correspond to sides. So zigzag loops correspond to points in infinity. Well, now I'm using this correspondence to say that actually these points of infinity correspond to these sides are not arbitrary. There are certain relations between them. And namely, for example, I consider let's consider the function lambda. So the lambda is just a function on my curve, one particular function. And this function has 0 at A, has pole at the one, maybe I should use another picture, sorry, it's more bit clear. The function lambda has pole at this point, pole at this point, 0 at this point, and 0 at this point. Therefore, you have a relation between these points at infinity in the Jacobian. So this is a principal divisor. So now, another thing, that instead of considering points at points on the curve, I just, by the same letter, excuse me for abusing notation, but the same letters, I denote the points in the Jacobian of the curve. So, or pick one, actually, of the curve. So I have a relation that the minus a minus b plus c plus d equals 0, just because by definition of the divisor of a function is 0 in the Jacobian. And the same thing about a minus b minus c plus d equals 0. So therefore, I have my integrable system gives me an elliptic curve and 4 points on this curve, but not any points, but points satisfying certain relation in the Jacobian. Since in this particular case, the Jacobian is just the curve itself, coincides with the curve itself, you can solve this equation very easily. For example, you can put, using homogeneity you can put d equals 0, b equals 1/2, and c equals a plus 1/2, for example. Well, so in fact, you have only two parameters. First is just the modules of the curve, and second is this variable a. Now,
By 1/2, do you mean theory characteristic or what?
no, 1/2 it means I imagine the elliptic curve is just quotient of the plane by 1 comma tau, and 1/2 is just 1/2.
How do you know which one is A and which one is A cycle and which one is B cycle?
I have chosen a cycle in such a way that b be equal to 1/2. It's a two torsion point of the curve, and I just it's my degree of freedom to choose the coordinates. Thank you for the question, definitely. So you can solve this equation. So now my aim is just to explicitly write solutions of this integrable system. So I explained that this system, well, I have this map from my C star to certain power to the base, and the inverse image is the Jacobian of a curve. And I want to go other way around. Suppose I have a curve, I have a point of the Jacobian, and I want to construct explicitly the coordinates which give this point. So it's essentially the solving integrable system. For example, in my new coordinates, the flows generated by Hamiltonians will be just moving, constant, steady move along the Jacobian. So it will solve I transform my complicated integrable system just to linear integrable system. And for that, I need also a little bit of combinatorics, which is called the discrete Abel map. And this is a map which takes faces of my graph and associates divisors of the Picard variety of the curve. And this is a very natural map. So you draw your zigzags, then you take one face of your choice and put 0 in it. And then every time you go to another face, you do the following. You just consider which zigzags you cross. Here you cross the yellow zigzag and the blue zigzag. But the yellow zigzag is oriented from right to left, and the blue zigzag is from left to right. So if you cross, you add the white zigzag that maybe you don't remember, but it was called A, and you subtract another zigzag. And so you keep going, and you can label all your faces, and well, due to the fact that due to the equation which I mentioned among ABCD, after substituting this relation, is actually the labeling is unambiguous. So if you keep going, if you go there, you get another time A, and if you get there, you get another time 0. So you can easily check that. Really, you can label your faces by divisors, and then you can write explicitly the solution, so you can explicitly parameterize your phase space by point of the Jacobian and by points of the Jacobian. So the general formula is, in this particular case, is simpler than the formula in the example. So this is the formula X can be expressed in terms of theta functions. So Zi is just a discrete Abel map in the ith phase. J is of J phase. Theta E is an arbitrary even theta function, Riemann theta function. O is, well, more or less arbitrary, well, some restriction, but with some particular, I do not want to go to details. Well, sorry, theta O is arbitrary odd theta function, and theta E is some particular even theta function. So you take this expression, the ratio of two theta function, and raise to the power epsilon ij. Epsilon ij is just another way to write it this Poisson structure. So Poisson structure is, you know, this variety is given by this formula xi xj equals to xi times xj times some number, which was, in my examples, either 2 or 0. So therefore, you just raise into this number to a Poisson given by Poisson structure and just multiply over. For this particular example, the Poisson structure is given by this picture, and the answer for example, for the x variable will be the product of four theta functions, or, well, squares of 4 theta functions. Well, you for example, x variable stands here, so you have to the right or to the left, you have a, well, you have a, you have here a minus t. Well, this is kind of straightforward way to write down the solution. And also, if you want to know the answer, it's very easy to check it, but just to say that it's a consequence of the famous phase trisecond identity. So the fact that really, if you make these variables and make all this procedure and substitute it into the original equation, you get the solution, is a simple manifestation of phase trisecond identity. So you really need to have theta function coming from Riemann surface and not arbitrary abelian variety. So some other properties of this, well, I will say a few, well, what is nice about this system that along with discrete, with continuous well, evolution given by Hamiltonians, have also discrete. And the discrete is actually coming from cluster structure. Well, here is, it comes from the fact that you can modify the graph and without changing the integrable system. And it's fortunate, because making such modification, you can pass from the graph to itself, but it gives you a non-trivial evolution. So the modification we can do are just very simple. One you can retract any two-valent vertex. But there is one non-trivial transformation that if you have a square, then you can make make such transformation. But in order to not to modify the spectral data, the equation of the spectral curve, for example, you need to change variables on the phases. And this variable change, well, it's manifestation of cluster structure, which I don't know to speak about right away, but for those who know what is cluster transformation, cluster mutation, it is it. So it's just some standard way to transform variables in cluster business. Now, how one can define the floor? And well, the theorem is that the equation of spectral curve, nothing, spectral data do not change under this transformation. How to apply that for our problem? For example, we can do well, actually two such transformations at the same time. Of course, the original graph and this graph are different. Then I can just contract these small edges and get another picture. So I pass from this picture to this picture. You have the picture is the same, but the variables have changed. So you have a transformation which is just automorphism of an integral system. Of course, this automorphism is just also some particular case of evolution character. So it corresponds to a certain shift in my variables. But this is an algebraic transformation, not well, the evolution, usually evolution operator is very transcendental function. Here is algebraic transformation. And there are discrete folds. It's possible to, in this particular case, the group of discrete folds is just generated by this transformation. And by very simple transformation, which you just go x goes to z and y to w. It corresponds to just a shift of this picture diagonally by one step. And of course, it's squared, it's small. So, and this group is nothing but the group in the Picard variety, in the Jacobian, generated by this ABCD. You remember there was equations connecting ABCD. So if you just quotient free group generated by that, by this relation, you get exactly z times z over 2. So this discrete transformation is just a shift on the Jacobian, but by subgroup generated by points at infinity. It's very natural algebraic, from algebraic geometry point of view, very simple construction. So, well, maybe I will not go into big details, I have no time, but I want to say that this integrable system, well, bad news or good news, that this integrable system is nothing new. Actually, this integrable system were quite known, though they were described in a much more complicated way usually. Because they actually, the integrable systems on Poisson leaves on Poisson-Lie groups, namely for PSLN. And in this particular case, it's PSL2. Well, there is a way to write it down. Well, maybe I should. There is some particular way how one can write down this determinant of D as actually a characteristic determinant of some matrix depending on lambda, which is more for connoisseurs. This is a more standard way to write the integrable system on standard integrable system on Lie groups. And so, therefore, but well, this approach is somehow, since it's first approach, which is gives that it turns out that many different Lie groups give the same different subjectively give actually isomorphic integrable system, and also, well, it gives the construction of integrable system in a way which is simpler than it's simpler than the original. So. And, well, to finish with, I would like to say a few words about generalization and perspectives. So first, think that this integrable system gives kind of relativistic in the sense that it has variables like not the momenta, but exponential of momenta, and so the final shift operators or something like that. So the limit to standard system, for example, standard Taylor system, is kind of non-trivial. But, well, it also can be done. Second thing, that, well, this is our purely finite-dimensional integrable system, but it turns out that the system like KdV, for example, are particular cases of this system, but in a certain limit. So if you take a Newton polygon, and you take a polygon which is for fixed width, for example, 2, and you take it limit, then the height goes to infinity. Then you get, for example, a KdV out of that. So this is KdV is kind of limit of the system, that size of the polygon at infinity in one direction. Very good question about if you start with torus, but not with torus, and but with surface of high Arrhenius. This is possible to do, definitely. Just well. There are some integrable systems not yet identified. This is possible. There is a way to get around. And well, another system that so this system cover many cases, in particular many system of known integrable systems, but one class is not covered. It's Hitchens systems. But what to say that there is also some recent progress in this direction, and some things can be done. And, well, there is a description similar to that, to Hitchens system, but not exactly. So there is a small. And the last comment that is a quantization is a cluster description. Well, I do not go to details, but the quantization is kind of arithmetic. So once you can easily quantize it. And all that can be quantum in the sense of quantum deformation. But of course, the question of that diagonalization of Hamiltonians in quantum version is another question. So it's not equivalent to the classical one. And this is the question, but also there is some progress in this direction, which I hope to. It will. Well, since the problem is really simple, and maybe I should say also that, for example, for this particular example, the equation, quantum equation you get, coincides with the equation which was considered by Professor Avila in his talk. So this Schrödinger equation with aperiodic differential is actually a particular case of this integrable system. So I hope that merging these two approaches could shed some light on the integrable system in general. So, okay. Thank you very much.
So we only have time for one question.
So you mentioned that you are getting particular leaves in this loop group from this construction. Would you be getting all suitable leaves for?
Well, these leaves correspond to, well, leaves are numerated by elements of the Weinberg group, by fine Weinberg group. So these leaves correspond to the cyclically reduced elements of the Weinberg group. It's just that.
Okay, thank you.
So, dear for local organizer, here's your mystery box.